By the way, today's class will be a short class. I have some work. I'll just try to complete the topic we started in the last class. So last time we were trying to build up the components of a neural membrane in order to understand the origin of the electrical signal. That is, how is the action potential generated? So first of all, how is the membrane potential generated? Right, and we looked at nuance potential and all that. And then how is the action potential generated? So we said that these are the important ions in a neural membrane, the sodium, potassium, and all that. And so depending upon the ionic gradient, you get a potential which is called the Nernst potential. Right, and every channel, there are these things called ion channels, which are selectively permeable to different kinds of ions. So a given channel can be represented as a series of a conductance and a battery or a voltage, where the voltage corresponds to the Nernst potential. And the conductance is the conductance of the channel. Now the conductance is can be variable if it is a voltage dependent channel, because channel gating means you'll be able to open or close the channel. That is, it acts like a gate. So when you're so when you open or close the channel, you are changing its conductance. When it's open, it has high conductance. When it is closed, it has low conductance. So that ability to vary a channel conductance is indicated by that arrow symbol, right, cutting across the conductance. So we said that for potassium, the Nernst potential is -77, right, and for sodium it is +50. So if you have only sodium channels, and if you have the standard distribution of concentrations between inside and outside for sodium, then you will have a Nernst potential of 50. And if you have only potassium channels, and if you have standard distribution of potassium between inside and outside, then you'll have -77. So all the voltages are referred to excuse me, from inside to outside, but that's a convention. So therefore you have then you have a third category of channel. It's not one channel, but lots of different channels. The common property to all of them is that they are constant. They cannot be gated. So therefore you can represent them as simply parallel branches of some conductance and a battery, and using what is called the Thevenin equivalent theorem, or Thevenin's theorem, which you study in your kind of high school electrical circuit theory. We can show that you can combine all of them into just one branch, and that one branch is called the leakage channel. Just a conceptual term. It's actually a common term for a whole class of channels. So then, in addition to all these channels, you have the cell membrane, which is a lipid bilayer, right? And there are two layers of these lipid molecules, two sheets of lipid molecules. And since it is an insulator, it acts like a capacitor, a parallel plate capacitor. If you look at a small patch of the neural membrane with these two sheets sitting there, it acts like a parallel plate capacitor. So if you want to electrically represent a small patch of the neural membrane, you can represent it like this. The membrane itself can be represented as a capacitor, like I just said. Then the sodium conductances or sodium channels can be represented as a series of a conductance and a battery, the GNA and ENA. Potassium channels can be represented as, again, another conductance and another battery, GK and EK. Then all other constant channels, right, which don't vary, they can be represented as a series of GL and EL. So this is, all of them are in parallel because all these structures sit across the same voltage difference between inside and outside, between the cytosol as the intercellular space and the extracellular space. So therefore, they have a common voltage, and therefore they're all in parallel. So now the actual equations of this whole circuit is very complex, because the variation of GNA and GK as a function of the voltage, we said they are voltage dependent, but the manner in which they vary is quite complicated. I won't get into all that because this is not a mathematical course. But I'll just give a very intuitive kind of back of the envelope calculation, just to understand the intuition behind how this voltage changes. And particularly, how does it change in the case of action potential? So suppose you take resting conditions. So let us say the whole circuit is in resting condition, all the voltages are constant, all the currents are constant. Then you can show very easily that Vm is given by this formula. Right, and now you consider a case where mostly potassium channels are open and sodium channels are closed. Then GNA is much less than GK, GL is much less than GK. Right, if you plug it into, we have seen this in the last class, we plug it into this formula, you get Vm is equal to approximately GK EK by GK, which is equal to EK. So EK is a negative value, minus 77 millivolts, but this is an approximate formula, and actually VM tends to be about minus 70 millivolts. It's a resting potential. So the resting potential is dominated by the open potassium channels and the fact that there are lots of open potassium channels and a few sodium channels. When the neuron gets into excited state, so then what happens is lots of sodium channels open and the potassium channels closed. So if you plug these numbers, GK is much less than, so GNA is much greater than other two conductances, basically. If you plug that into this formula, then you get VM is equal to approximately GNA, ENA by GNA, so which is equal to ENA. So therefore, V is close to ENA, which is 50 millivolts, right? So it becomes close to a positive value. So actually, this is, since it's an approximation, it goes up to about 30 millivolts. So also the thing is, during action potential, it is not in steady state condition because it's a highly dynamic condition. These calculations are just to give an intuitive idea. These are actually very approximate, and you cannot take it too seriously. The only intuitive idea I'm trying to convey with these calculations is that when you open sodium channels, the voltage goes up. When you open potassium channels, the voltage goes down. And this is the way it is because the manner in which the sodium potassium concentrations are constantly maintained between inside and outside. So like I was saying, there is more sodium outside and less inside. There's more potassium inside, less outside. And when the channels open, actually there is a flux of sodium from in both directions. So when the channels open, sodium goes from outside to inside because it's high outside. Similarly, when the potassium channels open, so potassium goes from inside to outside because it is high inside. So when these changes take place in both the intercellular space and extracellular space, there are separate molecular mechanisms which will make sure that these changes are quickly reverted. That is, whatever buildup of potassium is happening in the extracellular space, all that is pushed back into the neuron so that it goes back to the original distribution. Similarly, whatever buildup of sodium is happening inside the neuron, it is also thrown out again by a different kind of molecules, so as to restore this standard ion concentration distribution between inside and outside. As you can easily see that this is most critical for a neuron's function. So it is very important to maintain the concentration levels of sodium and potassium in the ECS and ICS at standard levels all the time. So when the neuron is operating and it is firing, these values are disturbed, but very quickly there are molecular mechanisms which are in place which constantly correct them. Right? It's like going in a leaky boat. Constantly water is leaking inside the boat, and somebody is taking a small tumbler and constantly pouring the water out, or something like that is going on here. So that is the logic behind the action of sodium potassium ion channels. Now we were saying that the soma, or actually is a particular part of the soma called the axon hillock, which is roughly here. So there, that is where the action potential is generated, because that is where you have a high concentration of voltage-dependent sodium potassium channels. In fact, that is the basis of action potential generation, because you need this kind of a voltage-dependent channels, to produce action potential. So, like I was saying earlier in I think 2 classes ago, that if you give a pulse current as input to the neuron, then in response to that, you'll have a voltage pulse as a response. As increase the current pulse, voltage pulse also increases. But once the current pulse goes beyond a threshold, the increase in voltage doesn't increase linearly anymore. It suddenly shows a very sharp nonlinear response, producing this action potential, this sharp increase and sharp fall. Okay, why does it happen? Because I was just saying that it happens because there are lots of voltage dependent sodium potassium channels. So basically what happens is the cycle goes like this. You first inject the current, which is this current pulse that you're injecting here. Okay, and then that will increase the voltage, because this is like a parallel plate capacitor. Increase the charge and voltage goes up. Right, and then when you increase the voltage, so we know that sodium channels open, because sodium channels are voltage dependent channels, and their property is, so here it is two ways. If you open sodium channels, the voltage goes up. And contrarily, if you increase the voltage, sodium channels open. So it works both directions. So sodium channels open up. and that will increase the voltage further, right? And in the process, potassium channels are also voltage dependent. So the thing is, when the voltage goes up, the potassium channels open. But the problem is when the potassium channels open, voltage goes down. So there is a complicated, positive and negative feedbacks going on here. That's why I said it's the actual dynamics of action potential generation is quite complicated. Equations look quite complicated, but I don't want to go into the math. I just want to give an intuitive idea in this course. So once sodium channels open, voltage goes up. Once potassium channels open, voltage goes down, because we have seen that. That's the nature of potassium channels. And that will reduce the voltage, and it will come back to the normal membrane potential. So this is how it looks. So when you inject a current, like a current pulse, let us say this is the input, and I inject some current pulse. Because of that, so I call this I of t. So because of that, the voltage starts increasing, and as the voltage starts increasing, that will open more sodium channels, and that will increase the voltage further, and that will open more sodium channels. So there is a positive feedback, right, happening here, and it will go very high, but it can't breach the ENA value because it's the upper limit. Okay, so it goes to a point. In the meantime, potassium channels start opening. So when the potassium channels start opening, the voltage goes down because that's the nature of the potassium channels, right? And so the voltage goes down. Okay, so this first part is where voltage gated sodium channels open, and the second part is where voltage gated potassium channels open, and the third part is where sodium channels are now closed, but the potassium channels are still open. So therefore, you have it goes even. So in the resting condition, there is some balance between sodium and potassium channels. In this case, where it is said to be hyperpolarized, or it's a hyperpolarization phase, right? The voltage goes even less than your normal resting condition. That is when you have a lot more potassium channels open compared to sodium channels. So therefore, it goes even less than the baseline value. And once it comes back to normal. Now, intuitively, this whole thing can be given a slightly disgusting analogy from real world, and it's actually a toilet flush is it's a very interesting engineering contraption, because as you have might have played with it at some point, and you would realize that if you turn the knob slightly, right, not fully down, then nothing will happen. There'll be a little trickle of water and nothing will happen. Okay, and but if you turn it so as you keep on turning it by different amplitudes, once you turn it beyond some threshold amplitude, then suddenly your whole hell breaks loose and all the water gushes down, and the work gets done, right? So that is a very good example. It's like so basically in the neuron, it's as though there is a energy that is held in storage, right? And the trigger, which is coming from the current from outside, is once it crosses a threshold, it will discharge that energy. Okay, and the discharging happens in the form of an action potential. Once the energy is discharged, neuron becomes quiet again. And sometimes, typically, what happens is neuron fires again and again until all the charge is discharged, and then neuron has to get charged again before it can be excited by an external stimulus. So all these what we have just discussed has been worked out by Hodgkin and Huxley, a British physiologist, and they got a Nobel Prize for this work in 1963. So if you simplify this whole thing, if you don't want to get very deep into what happens inside the channels and what are the currents and what is the conductances and all that stuff, just look at it from a high level, like a bird's eye view, like an engineer. Right? My input is a current of some amplitude. Output is a voltage of certain other amplitude. Okay, as the input current amplitude goes up gradually, right, my voltage amplitude also goes up gradually, pretty linearly. Once my input current amplitude goes beyond a threshold value, after that the current amplitude shoots to a sharp, right, a positive value, this level. After that, there's no change; it remains flat. So obviously, I'm really simplifying it, but the voltage current relationship is nonlinear. It's not like a linear straight line. It's like a step, more or less. It's like a step. Until that point, there is very little or no response, and beyond that, suddenly there is like a step-like response. It's nonlinear. So the current voltage relationship is nonlinear at the ion channel level. What is interesting is this nonlinearity that is happening at the level of single channels is what gets translated into a nonlinear relationship at the level of a whole channel, a whole neuron. Why is the ion channel at the level of ion channel current voltage relationship is nonlinear? Because we think of this voltage dependent, right, ion channels. Okay, it's a voltage dependent conductance, right? So we all know what is Ohm's law. Okay. So that means if you plot V against I, it's a straight line. So this is a linear relationship. So this is a linear resistor, linear conductance. But if you say the conductance is itself dependent on voltage, so I'll write this as I equal to GV, right, where G is the conductance. And if I say G itself is a function of voltage, which is equal to G of V times V, then my whether it is V versus I or I versus V, right, it's not going to be a straight line. It will be some complicated thing. Okay, so it's a nonlinear relationship. So at the moment you have something like voltage dependent ion channels, which are conductances, right? Then at the level of the element, circuit element itself, we have nonlinearity. And so therefore a circuit which is made up of nonlinear elements like this, right? So this is nonlinear. Okay, this is also nonlinear. So therefore, in this circuit, if I inject some current, if I measure the voltage Vm, obviously it's going to have a complicated nonlinear response. It won't be linear, right? Yeah, so this nonlinearity at the level of single ion channel is what gets translated into nonlinearity at the level of the whole neuron. So like I was saying, if I have an ohmic conductance or an ohmic resistance, the I versus V relationship is linear. If a non-ohmic conductance, then it will be nonlinear. So that's what is happening here. So the nonlinearity at level of single ion channel is showing up in terms of the response of the whole neuron to current like this. So output voltage amplitude, input voltage current amplitude is some kind of a nonlinear function like this. You can approximate it as a step function, but anyway, that's a small detail. No, at this point, you can compare the neuron with electronic circuits. Because if you look at circuits, if you have done some course on electrical circuits in your first year, like the basic electrical engineering or something like that, or you have done some circuits in your high school up to +2, right? So then you would have studied what is a battery, what is Ohm's law, what are resistors, capacitors, inductors, and all that. I mean, they're all linear. Okay, because all the equations are linear. They're differential equations, but they are linear differential equations. But the moment you go to electronic circuits, right, the BJTs and FETs and op amps, and you might have studied some of them, they're all nonlinear. Okay, so if you operate them in a small operating range, they look linear in that small range. But if you increase the range, obviously they are nonlinear. Because even a curve, and look at it over a small range, it looks linear. But if you expand the range, it will reveal its nonlinearity. So your transistors or basic electronic circuits are all nonlinear. And that is what has led to the computer evolution. I mean, you could not have built a modern computer with simply RLC or resistor, capacitor, and inductor kind of circuits. It's not possible, right? You needed to have this kind of nonlinear devices, which are switches, which is what the transistors are. So similarly, imagine if a neuron doesn't have voltage dependent sodium potassium channels, right? And then it will be a pretty pathetic neuron in terms of its computing abilities. Because first of all, the action potential propagation on the axon will be pretty poor. It will just quickly die off, and it cannot go to long distances because this is not a electronic current; it is a ionic current, right? So it will die off very quickly. But because it has all this myelin sheath, and also there are these voltage dependent, ion channels, sodium potassium, the signal gets charged up, and that's how you have an intact signal traveling from one point to another. And this is kind of like your digital signal. I mean, digital signal has a very different shape. Digital signal is like a rectangular pulse. But whereas the action potential in a neuron is like a sharp, spike, almost like a delta function. So that way it is different, but point is its shape is kept intact. So normally speaking, if you had a passive cable, that pulse will lose its amplitude and start spreading and will lose its shape. But because you have this voltage sensitive channels, right, it starts getting charged up. So here one point that's important to notice is the voltage sensitive channels act like sources of energy, right? It is because of this nonlinearity acts like a source of energy, and that's why even in electronics, right, you have, let's say, amplifiers. Amplifier means what? You take a weak signal and amplify it. That means you're injecting energy into the signal without changing signal shape. How is it possible? Because of the electronic circuits, right? You cannot amplify signals using a passive circuit with RLC circuit, right? So you need nonlinearity to amplify it. Okay, so this is a simple example, a biological example of how you get amplification, or you get this kind of a recharging of the signal at every point as it's propagating, simply because you have these nonlinear elements inside the cable. The reason I'm putting it like this is because, so generally when you study biology or when you study neuroscience, you get lost in the biological detail. It'll be nice to understand the mathematical essence of it. Why is there some special property in the system? What is at the root of it? And we need to understand it without getting lost in the details. Here, the root property is this nonlinearity at the level of the conductances, the ion channels. So in the axon, as the signal is propagating, you have these myelin sheaths, which are actually different kind of cells. So in the CNS or central nervous system, this myelin sheath is supplied by a kind of glial cells called oligodendrocytes, and in PNS they are supplied by Schwann cells. Okay, so that is what they are. So these increase the resistance, increase insulation. So therefore, there is not much leakage of the current as the signal propagates through the axon inside, which kind of runs inside it. In addition, there are all these sodium potassium voltage sensitive channels inside the cable that will act like a source of energy, so it will keep recharging. So because of this very special arrangement, very nicely designed engineering system, if you look at a cable which has myelin sheath, especially a thick cable which has myelin sheath, diameter can be, this has been microns, okay, 6 to 12 microns, and so the speed can be 35 to 75 meters per second. Sometimes it can even go to 100 meters per second. So basically, it's not a very fast signal compared to electrical signals in a metal wire, right? And then you have thin myelinated cables, which are myelinated, but they are thin cables. Diameter is only about 3 microns. Here, the speed is about 3 to 15 meters per second. And then you have unmyelinated cables. This is called type C. The first one is type A and second is type B. These have much smaller diameter, right? And the speeds are also very low. So usually the myelinated cables are used to convey sensory motor information, because the unmyelinated cables are used, or fibers are used for conveying pain information, which propagates a bit slow. Now, so this picture just shows how the signal propagates along an axon. So you have this increased voltage, this red patch is increased voltage, so that propagates down the thing. Now, there's a property that relates the thickness of the cable with the velocity of propagation. So if you have a thicker cable, velocity also is higher. We have seen that even in this table, right? Thicker cables means higher velocity. And because of this myelin sheath, velocity is higher even in this, particularly in this section of the cable. But once the signal goes out to a small section, these are called the nodes of Ranvier. They're called nodes of Ranvier. So within that part, there is no myelin sheath, so signal slows down a little bit. And again, once it goes under the myelin sheath, it speeds up. So if you kind of look at it in a slow motion, it looks as the signal propagates fast under the myelin sheath and slows down a little, propagates fast again, slows down again. So it looks as if it is jumping from one node of Ranvier to the next node of Ranvier. It's just a more, I would say, it's more like a poetic way of describing this propagation. So this kind of a conduction is called saltatory conduction. Here saltatory doesn't have anything to do with salt. It just means it's a jumping conduction. So action potential jumps from node to node. It's just a way of talking about it. Next, next we are left with what happens at the synapse, right? How does signal go from one neuron to another? So last time we have just said that there is a synapse. Right, the synapse, you have a presynaptic terminal from the axon of one neuron coming very close in close apposition to the postsynaptic terminal of another neuron. So action potential comes to the presynaptic terminal, and then something happens here, and that produces a postsynaptic potential on the other side, right? And how does this happen? So here there are three molecules involved in this transmission of signal from pre to post. The three molecules are the neurotransmitter, which is released by the presynaptic terminal, then a receptor, which is located on the postsynaptic terminal, right? And then the receptor on the postsynaptic terminal then opens or closes an ion channel. So there are three molecules, NTS, then a receptor, and an IC, ion channel. So these are three molecules which play a crucial role in converting the signal from the presynaptic side to the postsynaptic side. So since there are three molecules in play, it's a chemical process. So how does it happen? It's a long story because the neurotransmission is an extremely complicated phenomenon, and molecular biologists keep on studying this in great detail. People who have spent decades studying just one kind of receptor, you can imagine what kind of complexity exists. So this kind of complexity may not be new to biology students, but for those of you who come from engineering like me, that might be quite shocking how a single molecule can be that complicated. Okay, so on the presynaptic side, this is the button of an axon, and inside this button, this neurotransmitter chemical is held inside small packets. So these packets are called vesicles. So vesicles, and each vesicle has typically about a few thousand molecules of this neurotransmitter. So when the action potential comes to the button, that's a trigger for neurotransmission. So this yellow kind of patch indicates the increased voltage. That's how the nerve impulses come here. That voltage signal will open certain calcium channels, which is not shown in this picture. So because when that happens, calcium rushes in, calcium ions from outside rush in. Now these vesicles are held inside a protein matrix, okay, like a network of proteins which hold them like that without moving. When the calcium comes in, all these bonds are snapped, and these fellows, for whatever reason, they start drifting towards the synapse. Okay, all these fellows, and so once they go to the synapse, as you can see in the right side, they open up. The synapses open up, and they spill their contents into the synaptic cleft. So this gap between the two terminals is the synaptic cleft. So the vesicles spill their contents into the synaptic cleft. All these neurotransmitter molecules now start diffusing across the small gap of the synaptic cleft and start going to the other side. And once they go to the other side, just a second. Once they go to the other side, on the other side you have these ion channels, like our familiar ion channels. Now, like I was saying earlier, I think a part of the ion channel itself acts like a receptor, which can receive this neurotransmitter molecule, which is coming in from the other side. Right now, think of the synaptic cleft as a river, and then it has two banks, the pre side and the post side. So these fellows are coming from the other side of the river. They come and attach to the receptor, which is located inside, right, this ion channel. Once a binding takes place, which is what you see on the right side, the channel opens and it will allow passage of ions. So if it happens to be a sodium channel, it will allow sodium going from outside to inside. If it happens to be a potassium channel, it will allow potassium to go from inside to outside. Okay, so the response could vary depending upon what kind of channel it is. But what is interesting is there is a kind of a one-to-one correspondence between the neurotransmitter and the channel. A given neurotransmitter can only attach to a certain kind of receptor, and that receptor will be located only on certain kind of ion channel. So this will make the relationship between the signaling between pre and post sites very specific. It's like a hotline between two people. Okay, so let us see a little bit more of that. Now these receptors, again, there are two kinds of receptors. These are called ionotropic and metabotropic, which can be seen in this picture. So what you have just seen is actually a special kind of receptor called the ionotropic receptor. So in this case, a part of the channel itself has kind of the facility to receive an incoming neurotransmitter, and it will respond to it by opening. All this happens within. Okay, it's like in situ. Whereas in different kind of receptor called the metabotropic receptor, the reception takes place in one place, and the ionic channel response, opening of the channel, happens in a different place. So, for example, here this is a receptor, a whole different molecule which sits inside the membrane. The neurotransmitter coming in. Okay, so there is a so the neurotransmitter and the receptor have some kind of a lock and key arrangement. Right. So once the kind of key matches with the lock, the receptor generates some signals. These signals go into the cell, right, and then these molecules actually can go through a series of stages. So it can be very complicated, and then finally act on an ion channel, and the ion channel will open. Okay, so this is called a metabotropic receptor, and generally the ionotropic receptor response are fast. Metabotropic are much slower. And also metabolic receptor, in addition to opening a channel which is also located in the same membrane, maybe at a distance, these signals can also go deep into the cell and have all sorts of action inside the cell. Like, for example, it can change gene expression. So these kinds of signaling pathways are called second messenger signaling. Okay, so it's a huge field in molecular biology, and I'm not an expert in that. But if you're interested, you can look up more on that. Now, to understand this difference, I would like to give a small analogy from your cafeteria, okay, which is quite a silly real-world analogy. So if you might have gone to our staff canteen, right? In staff canteen, if you want to buy coffee, you have to pay in one place in the counter, and the guy will give you a token, and you give the token in a far-off place, and then the guy will give you a coffee or tea. So that is like your metabotropic receptor. Okay, you pay here, and then you take the signal and have the action at a remote place. And generally, in a lot of cafeterias, small ones especially, you pay in a given place, and immediately the guy will give you coffee. That is like the ionotropic receptor. I just thought it's a silly analogy, which it's fun to know that. So now, like I said last time, that there are two kinds of synapses. So all synapses produce a PSP, but some produce an excitatory PSP, others produce inhibitory PSP. The difference comes, it depends, it depends on what kind of channels open on the postsynaptic side. So let us say this presynaptic fellow releases some chemical. If this chemical lands on the sodium channel and opens it, then sodium ions rush in, and the voltage will go up. So that is, then you get an EPSP. And a neurotransmitter, a typical neurotransmitter, right, released by the presynaptic side, which has this kind of action, is glutamate. So, and such a neurotransmitter is called an excitatory neurotransmitter. And glutamate is a very typical, example of an excitatory neurotransmitter, and found pretty much everywhere in the brain. Then the other kinds of neurotransmitters, where when they act on the ion channels, they act on either potassium or chloride channels. See, potassium ions are positive, chloride are negative. But thing is, when you open a potassium channel, potassium goes from inside to outside. So therefore, it creates a negative voltage. When you open a chloride channel, chloride goes from outside to inside, and that's the nature, because that's how the distributions are maintained. So in both cases, sodium, potassium, and chloride, the effect of opening the channel is to reduce the voltage, to take it to more negative levels. So one standard neurotransmitter, typical neurotransmitter, which has this kind of an effect, is called GABA, which stands for gamma aminobutyric acid. So thing is, so there are different neurotransmitters that come in two categories: excitatory, inhibitory, and they have receptors, and receptors are connected to certain ion channels. So thing is, so this relationship between neurotransmitter and receptor is not a simple one-to-one relationship. Things can be a bit complicated. So a given transmitter can have multiple receptors. So for example, glutamate has three receptors, AMPA, NMDA, and kainate. And NMDA is a very important receptor which is involved in memory and learning and all that. But it's a big story. I'll maybe come to that later on in the course. And so once this binding takes place, what kind of channels open? If it is the first one, AMPA, then it opens sodium alone. If it's NMDA, it opens sodium and sodium, but it's a channel which allows both sodium and calcium. It's a double channel. Kainate allows both sodium and potassium, which is kind of conflicting, but that's the nature of this channel. This receptor opens both the sodium and potassium channels. So GABA, on the other hand, is inhibitory, and it has actually two receptors, GABA A and GABA B. Some are missing here, right? And GABA A opens chloride channels. So here again we have one more idea, which is the strength of the synapse. That is, if the response of the synapse to a given action potential is a high PSP with large amplitude, you can say that the synapse is a strong synapse. But if the response is a small PSP, you can say that it is a weak synapse. In fact, also one more thing about synapse is the response is not completely deterministic. So every time you fire an impulse into the presynaptic side, there's no guarantee that the postsynaptic side responds with a PSP. Sometimes it does, sometimes it doesn't. So therefore, the response of the postsynaptic side is stochastic. Okay, if you look at a huge bundle of synapses, then the responses on average can be more predictable. But if you look at individual synapses, then the response is stochastic. So now let us wrap this up, right? We can say that, so when a neuron has inputs coming from many other neurons, and some are excitatory, so it's like this is excitatory, and this is inhibitory because the incoming PSP is negative, is also inhibitory. So in this case, the total input voltage into the soma is negative, so it doesn't get excited. So there's no firing, right? Whereas if you have a lot of excitatory signals coming in, right, and few inhibitory, then excitatory signals dominate the inhibitory, and so the overall effect of the excitatory signals on the neuron is to increase the voltage perhaps beyond the threshold, and when that happens, the neuron fires and sends us an action potential. So these are the action potentials. These then propagate down the axon. So this is like a very simplistic depiction of how neuron responds to inputs coming from other neurons. I mean, a real neuron is actually a lot more complicated. There are shades of differences in response, the differences in the response dynamics, and it's a whole zoo of neurons out there. But what we will do is to keep the story simple. We'll stick with this simplified depiction of the neuron, and we'll show how you can construct networks, right, slightly abstract networks out of such neuron model. Again, I'm not going to use much math because this course is a biology course. Okay, just quickly intuitively discuss some ideas. And once you understand how these networks work, just intuitive sense, we'll start applying those ideas to real brain. And let us see how we can understand real brain in terms of such network models. Okay, so to summarize, so we have seen that the input, net input, to a neuron to a response in terms of voltage amplitude is something like this, but I can idealize that into like a pure step. So this is where we'll start from the next class, and we'll define a simplified ideal neuron model, right? And then using such neuron model, we'll see how you can construct networks. And later on, we'll see how with such networks, you can explain a lot of phenomena happening in the real brain.